A new class of intelligent machines with self-regulating, event-driven process flows for designing, deploying, and managing distributed software applications. All biological systems have the ability to make sense of what they are observing fast enough to do something about it while they are still observing it. They do this using their inherited or learned behaviors made possible by the knowledge transferred through their genomes from the survivor to the successor. Both inherited and acquired knowledge play a crucial role in the system's behavior when events cause fluctuations in their interactions. Intelligence provides the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience. It's about understanding our surroundings, catching on, making sense of things, or figuring out what to do. Intelligence can be approximated by the ability to produce accurate predictions. Wisdom, on the other hand, involves an integration of knowledge, experience, and deep understanding, as well as a tolerance for the uncertainties caused by various events. It's about having an awareness of how things play out over time and conferring a sense of balance. Wisdom is often associated with balancing interests and goals, and it largely emerges from reflection on past experience. Knowledge is information that has been processed, understood, and internalized by an individual or a system. It goes beyond raw data and information to encompass insights, understanding, and the ability to apply information in a meaningful way. Knowledge is a higher level of cognitive processing compared to information. A pattern of behavior refers to recurring and predictable actions, reactions, or responses exhibited by individuals or systems in specific situations. Patterns of behavior can be observed in various contexts, such as human behavior, organizational behavior, or system behavior. They often emerge from a combination of individual and environmental factors. Knowledge can shape patterns of behavior, and recognizing patterns can contribute to the acquisition of knowledge by identifying regularities and trends in data and experiences. Intelligence is a complex and multifaceted concept that encompasses the ability to acquire, understand, apply knowledge, and adapt to new situations. It involves problem-solving, reasoning, learning, and the capacity to comprehend and navigate the environment effectively. Intelligence is often closely tied to the ability to recognize and interpret patterns. Intelligent systems, whether human or artificial, can identify meaningful patterns within data or experiences. Interpreting patterns is a crucial component of effective problem-solving. Intelligent systems can analyze patterns to make predictions, draw conclusions, and generate solutions to complex problems. Intelligence involves a range of cognitive abilities, and the capacity to interpret patterns is a key component of these abilities. Recognizing and understanding patterns in data or the environment is a fundamental aspect of problem-solving and decision-making, and it plays a significant role in both human and artificial intelligence. Wisdom involves a deep understanding of knowledge and the ability to apply that understanding judiciously in practical situations. Wisdom plays a crucial role in guiding decision-making. Wisdom involves the accumulation of knowledge and insights gained through experience. Learning from past experiences, both successes and failures, contributes to the development of wisdom. By reflecting on past events and understanding their outcomes, a wise individual can extract valuable lessons and principles that can be applied to similar situations in the future. Wisdom involves a temporal perspective, recognizing the dynamic nature of life and understanding that situations evolve over time. It acknowledges the importance of considering both short-term and long-term consequences when making decisions. Wisdom involves drawing on accumulated knowledge, learning from experiences, anticipating consequences, adapting to change, considering ethical implications, and balancing risks and rewards. It reflects a holistic and thoughtful approach to decision-making that goes beyond mere factual knowledge to incorporate a deeper understanding of the complexities of life. Human intelligence is instrumental in bringing people, processes, and technologies together to create businesses with a purpose and goal. Machine intelligence created by human intelligence is useful in improving efficiency, resiliency, and scalability through process automation and intelligent decision-making. The same set of data can be transformed into different information depending on the context in which it is used. Information is processed into knowledge and given context, allowing it to be meaningful, operational, and useful. Intelligence is instrumental in using knowledge to accomplish a purpose with a goal. Wisdom uses experience and meta-knowledge about the optimal paths to using knowledge from many paths to achieve the goal successfully while managing risks associated with them. The Turing machine schema is a sequence of symbols as programs are operating on a sequence of symbols as data structures. The structural machine schema is operations on knowledge structures. Knowledge structure is a process that receives information, executes the process, and shares information with other processes wired together as a knowledge network using shared knowledge. Wired processes fire together to execute autopoietic and cognitive behaviors encoded in the knowledge network. In the medical domain, data, information, and knowledge are used to create a model of the early diagnosis process when symptoms are presented by a patient to a healthcare provider. The process uses the medical knowledge captured by the large language models and other sources, event history, and provider analysis to make recommendations. Associative memory of the history of all events, transparent schema-based operations, and queries provide a new approach to using knowledge wisely, based on the meta-knowledge of best practices and optimal use. In this demonstration of a digital medical assistant, we start with our empty database on the left and our user interface on the right. To begin, we need to register a care provider to act as our doctor. When this registration is complete, we can see our first instance of our care provider vertex, along with the corresponding unique event vertex. Each event has a timestamp and holds the identification data for each actor in an event. To continue our process, a patient needs to be registered. Upon registration, a new vertex is added into our database to represent our patient. This is accompanied by another unique event vertex that is related to our patient. Now that both our patient and care provider are registered, we can have our care provider log in and select our patient based on unique identification or a medical record number. Once the identification is verified, an appointment event has occurred between the care provider and the patient, and a new event vertex is added into our database and related between the newly added vertices to represent our acting care provider and patient. The care provider is now able to access the data associated with our patient and is now able to take note of the current symptoms our patient is experiencing. Once those symptoms are entered, they are represented in our database as new vertices and related to our patient. As this process takes place, those same symptoms are sent to a knowledge acquisition process which uses LLMs and historical medical knowledge to hypothesize possible differential diagnoses. This hypothesis generates a new event and enters the hypothesized diseases as new vertices in our database. These diseases are related to the acting symptoms of the event, which indicates the possible disease diagnosis. As our care provider is presented with the differential diagnosis, they can select a disease to gain further insight. Upon this selection, the care provider is given a short synopsis of the disease, as well as a list of other diseases that are statistically significant based on our historical data. Each of these diseases are provided along with a p-value and a list of correlating symptoms that might also be present or become present as the patient's condition progresses. From this screen, our care provider is able to inspect key symptoms and risk factors to reinforce their decision. As key symptoms are generated, the results are added into our database under a new event and related to the relevant disease in which these new symptoms are key to determine a diagnosis. Our care provider can also generate risk factors based on the disease selected. These risk factors are then added into our database under a new event and related to the corresponding disease. If our patient exhibits any of these risk factors, those risks are related to the patient to further enforce a diagnostic decision. If they are sufficiently convinced, they can officially diagnose the disease. Upon diagnosis, a new event is created between the care provider and the diagnosed disease, and another event is created between the patient and the diagnosed disease. Each acting entity is related vertically to events in time and as well as related horizontally through time to show the progression of the network state. These events create trees of related data that can be queried and traversed to recall past states of the network. The data network that is produced can be viewed through two perspectives, as the event history and as an associative memory. Associative memory is a type of memory that allows the recall of information based on similarity or relatedness. Associative memory is a way of linking two pieces of information so that when one is activated or recalled, the other is also brought to mind. Neurons that are wired together fire together. Neural networks are inspired by the structure of the brain and are capable of learning and performing various tasks through interconnected layers of neurons. Associative memory concepts can be incorporated into neural network architectures to enhance their ability to recall and associate information. Event-driven systems respond to events in real time. This is beneficial for applications where immediate responses are required. Real-time updates and responses can enhance the performance of associative memory systems, allowing them to quickly adapt to changing patterns and associations. Events trigger actions, and the system adapts dynamically to these events. This is crucial in dynamic environments where patterns and associations evolve over time. Associative memory systems can benefit from dynamic learning, continuously updating associations based on real-world events. This is particularly useful in scenarios where associations change frequently. This presentation is about showing a new approach to creating transparent, model-based machine intelligence that captures the associative long-term memory based on event history. Associative memory plays a crucial role in reasoning. It allows individuals to make and then recall connections and inferences, even when those connections are not clearly explained or spelled out. The ability to form and recall associations between different pieces of information is fundamental to the reasoning process. It enables us to make connections between different pieces of information, draw inferences, and make predictions based on past experiences. This is particularly important in problem-solving and decision-making processes where we need to integrate and interpret diverse pieces of information. Queries allow new patterns to connect with past events in the process of reasoning. This concludes the presentation on event-driven architecture. Thank you for your time and attention.